Hey students, this lesson is on magnetic fields. So our goal for today is to start off with just the basics of magnetic fields. So what do they look like, how are they created, how we go about removing them if we wanted to. Now this is something that we talked about in class earlier, so if you were there and you felt really good about all this and don't need the review, feel free to skip a few minutes into this video. If you would like the review though, just stay tuned, keep watching. Alright, for the second half of the video though, we will be diving into some new stuff and using something called the right-hand rule, which we're basically going to find helps us to figure out how current and magnetic field direction are related. So we'll look at two different examples. First, just a wire, and second, a solenoid, which is sort of a special kind of wire. And we will talk about how to find magnetic field based on current or vice versa. So a little bit of a review of just the basics of magnets. I'm sure you played with them as a little kid, but we'll go into a little bit more detail here. Okay, now to start off, you may have noticed with all magnets they always have two poles, which by convention we call north and south. What we find is that if we bring two of the same poles from two different magnets together, so two north poles or two south poles, they will tend to repel each other. Whereas if we take a north pole from one magnet and a south pole from another magnet and bring them together, they will attract, much the same way that like charges repel and opposite charges attract. Okay. Now, I am hoping you never did this as a child, but if you were to take a magnet and break it in half right down the middle, what you might expect then is that we would have one piece that's a north pole and one piece that's a south pole. But actually, as it turns out, it doesn't work that way. What we find is if we break a magnet in half, each part becomes a new magnet with both a north and a south pole. Okay, so what this means and why this is interesting is that we have never, ever found a situation in which we have only a north pole by itself or only a south pole by itself. For some reason, what we always find is that north and south poles go together. Where there's one, there's got to be another as well. We have never had what we call magnetic monopoles, a situation where we just have one pole by itself without its opposite also attached to it. Kind of a weird little thing for you. Right? Now, that's all well and good, but, you know, where did these magnetic properties come from? Why are magnets magnetic? Now what it turns out is that magnetic fields basically arise from our atoms and our electrons. What we find is that anytime we have a charged particle moving, it's going to create a magnetic field, always. And as it turns out, all the little atoms in your body have electrons orbiting around them. Since electrons are charged particles and they are moving, they're creating magnetic fields, which means every single atom in your body right now has a magnetic field. Pretty weird. The reason that we don't tend to notice this, that we don't actually like see magnetic interact with magnets, is that even though all of our atoms have these magnetic fields, there's nothing really coercing them to all point in the same direction. Two atoms next to each other may have electrons that are orbiting around in totally different directions, and what we find then is that all these random magnetic fields kind of tend to balance each other out. Okay, this is kind of like the upper picture that you see right here, where we've got a material with all these different atoms, and the arrows indicate the direction of the magnetic field. Now sure, these clusters of atoms, which we call domains, may all kind of align to each other, but there's no overarching force that's kind of encouraging all of the magnetic fields to align to each other across the entire object. So what we find is that everything's kind of pointing in random directions, and in the end, they sort of all cancel out. And this is what's happening in your body right now. But there are certain materials that we can easily kind of convince all of the atoms to get their magnetic fields aligned the same way. Iron certainly is sort of the classic example of a material that can do that. So if we can create a magnetic field that's very compelling, or if luck just happens to be on our side and this is how it turns out, we can get all those domains aligned as we see in this bottom picture. Now once all of those magnetic fields of each of our atoms is pointing the same way, all the electrons are orbiting in the same fashion, we end up with something that behaves like a magnet. All right. Now, the same way that we can magnetize an object, get all those domains oriented in the same direction, we can also demagnetize an object. And basically anything that will scramble up those domains again and get the atoms sort of oriented in different directions will demagnetize the object. Now, if we just wait long enough, there will be a tendency for those atoms to kind of fall out of line, the same way that, you know, even though you make your room all nice and neat, over time it's going to, you know, get messy again. That's just sort of the natural order of things. But if we want to speed along that process, a few things that we could do. Number one, we could take a really strong magnetic field and put the magnet into that magnetic field and kind of shake it all around and stuff, so that some of the atoms reorient with the new magnetic field and some are still oriented with the old magnetic field, and everything gets jumbled up. So that's one way that we could do it. Another way that people tend not to think of is we could heat up our magnet to a really high temperature, because as an object gets heated up, its atoms vibrate and move faster and faster, and the faster that they're moving, the more likely it is that the electrons are kind of jumble up and get orbiting around in the wrong direction and kind of throw off that perfect organized magnetic field alignment. So by heating up our magnet, we can demagnetize it. And then, for lack of a better term, we could just kind of beat the heck out of it. So basically, if we mechanically apply a jarring enough force to our magnet, we can also get the atoms to kind of scramble up a little bit, get the electrons moving in the wrong direction, and demagnetize it. So a few ways that you can, you know, break your refrigerator magnets in case you ever wanted to do that for some reason. Okay. So if we wanted to then draw the magnetic field of a standard bar magnet, okay, what we would find is that it's a little bit different from like gravitational fields or electric fields, in that magnetic field lines form closed loops. Okay, so that means that they go around and around in circles over and over again, through the magnet and then out of the magnet again, and then back up through and then back down around again. And this is true for all magnetic fields. They always form these closed circles, basically, which is a little bit on the weird side. Now for a bar magnet, what we find is that those magnetic field lines point out of the North Pole, around again, and then back into the South Pole. Okay, so magnetic field always comes out of the north and back into the south. That's what we find. Obviously, writing magnetic field every time gets kind of long, so just so you know, we abbreviate magnetic field with a capital B. I know B's have nothing to do with the word magnet. That's just kind of how it turned out. Sorry, guys. So capital B indicates a magnetic field. Okay. So this is the basics of a bar magnet. I think we're all kind of comfortable with bar magnets and the fact that they are, you know, magnetized. But in class, what you hopefully have found at this point is that when we construct a circuit, we are also creating magnetic fields, because as I said, magnetic fields are created by moving charged particles. Now in the past we talked about how electrons are charged particles that are moving around the atoms, and so they created a magnetic field. But electricity also would be an example of charged particles moving. So anytime we have current flowing in any circuit, we're also creating a magnetic field. That means all throughout the last unit, when you are making all your circuits and designing your cereal boxes, you are making magnetic fields, and you didn't realize it. Funny that. Okay. So if we examine just a simple straight wire that's carrying a current, what we would find is that our compass needles would align to go around it in a loop. Okay, so we see that this wire here, if we imagine running a current through it, it would create a magnetic field that just forms a nice even circle around it. Okay. We can also see that here with these iron filings. They have aligned themselves to the magnetic field, forming these big circles whose center is always that current carrying wire right there. Okay. So now we know the shape of a magnetic field around a wire. It's just a circle with the wire in the middle. You might be wondering, though, whether that field goes clockwise around it or counterclockwise around it. And the way that we can figure that out is using something called the right-hand rule. Okay. Now, using the right-hand rule to determine magnetic field, for a wire, it's pretty simple. Basically, here's what you do. You take your thumb of your right hand. It's called the right hand rule because you use your right hand, never use your left hand. Right hand, okay? Thumb goes in the direction of the current, along the wire, whichever way the current is moving, okay? Once you've got your thumb in place, you wrap your fingers around the wire. Imagine doing that, okay? So it's kind of like you're making like a thumbs up or a thumbs down or whatever, or a fist, you know, whatever floats your boat. Okay. Now the direction that your fingers automatically curl in towards your palm is the direction of the magnetic field. So for this example right here, we see that the current is directed upward, so the thumb is pointed upward, and then the natural direction for the fingers to curl around shows us that the magnetic field goes to the right in front of the wire and to the left when it's in back of the wire. Obviously, this is the only way that your fingers can curl. They can't very well like curl around to the back of your hand. Okay, so they're always curling in towards the palm. They indicate the direction of the magnetic field. So if we apply that to the previous picture, what we see is that our magnetic field is always going around this way, so kind of in a counterclockwise fashion from our perspective. Okay, so we can also imagine then figuring out the direction of the current by aligning our fingers to the magnetic field. So if I curl my fingers around this way, counterclockwise, I see that my thumb kind of has to point upward. There isn't really a good way to curl them that way and have my thumb pointing downward. So that tells us then that for this particular wire, the current is pointing upward. Neat little trick. Look at that. All right. Now, we're going to try some more practice on this in class, but I want to introduce one other thing to you. So we can imagine, if we don't just want a straight wire, because straight wires are kind of boring, we could then twist the wire into a loop. Now, at each point along this loop, we have the same circular magnetic field all the way around, all the way around, all the way around, so that we end up with magnetic field lines that kind of look like a big donut. Okay, just making these little circles around the loop. And what you might notice is, funny, look at that. They're all coming out the top here and in the bottom here, which means that this looks like the magnetic field of a bar magnet. So by taking our simple wire and just looping it around into a circle, we've created something that behaves like a bar magnet with a north and south pole, the same kind that you used to play with as a kid. Weird. All right, so we've created something that looks like a bar magnet. If we wanted to add a little bit more power to it, we could simply add more loops around and around and around. We don't just have to go around once. We could, you know, continue twirl, 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 and back out again. If we do that, we create what is called a solenoid. Okay, so a solenoid is just a coil of wire that carries a current, and what we find is that the magnetic field produced by that solenoid looks like that of a bar magnet. Now, the same way that we were able to figure out the direction of the magnetic field using the right-hand rule with the wire, we can use the right-hand rule to figure out the direction of magnetic field with a solenoid as well, to figure out which side is essentially north and which side is essentially south. This is trickier. Okay, so I need you to stay with me on this one. This one's a little bit trickier, but if you just take your time with it and ask me questions when you need to, you're going to be fine. Okay, now here's my preferred method for figuring out the magnetic field for a solenoid. There are many ways. I would be happy to show them to you if this way doesn't work for you, but this is the one I've found to be the simplest in general. Okay. Your first step is to choose a point along the edge of the solenoid from your perspective. And we're going to go through an example of that in just a moment. So we'll choose one point on the edge. We'll figure out whether the current is traveling into the page or out of the page at that point. Figure out the direction of the current just at one point, ignoring the rest of the solenoid. Once we've figured that out, we can use our good old right hand rule to figure out what the magnetic field looks like just at that one point. All right. Once we've drawn that, as it turns out, that kind of shows us the direction of the magnetic field for the entire solenoid, just by analyzing one point on the solenoid. Okay, so anytime you're analyzing this, no matter which method you choose, I always want you to focus on one point on the solenoid at a time. So let's look at an example. Okay, so we have a solenoid here. Our current is coming in this way. It loops up in the front and then down in the back, up in the front, down in the back, up in the front, down in the back, blah, 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 until it comes back out. Now, this one, we already have the magnetic field lines drawn for you, but I'm going to show you how we were able to figure that out. Okay. Again, our first step is to choose one point on the edge of the solenoid. I'm going to choose this point right here, just this exact little point on the edge of the solenoid right in the middle. Okay. Now at this particular point, either my current is going into the page or it's coming out of the page. See how we're like right at the edge there, so it's either going in or coming out. Now if we follow the current along, we see again that it goes up in the front and then down in the back. Up in the front, down in the back. So if we imagine that happening, coming up in the front, right at the very top here, it's going perfectly into the page away from us. Okay? Feel free, obviously, to like do this with your hand, make it work. Okay? Imagine it going upward, and then as it curls around to go towards the back, it is going perfectly into the page at that moment. All right? Now, since we know that at this exact point right here, the current is going into the page, we can then use our right-hand rule. So let's point our thumb away from us into the page and curl our fingers around. And what we see is that our fingers curl clockwise. So what I'm going to do is just draw a magnetic field just around that one point, going clockwise. So since I know that the magnetic field is going into the page, that's how my thumb goes. My fingers are curling around in the direction shown. All right. Now it turns out that if at this point the magnetic field is clockwise, that means at every other point along the top here, the magnetic field is clockwise. Okay. Which means that we can basically just take this circle and make it bigger, extend it outward, and what we see is that these magnetic field lines here for the entire solenoid are the exact same thing. They're going clockwise around the top of the solenoid right here, which means that the magnetic field is going in on the right-hand side and out on the left-hand side. Back around, in on the right, out at the left. And that means then that the left-hand side is our north pole, since the magnetic field is always coming out of the north. And the right-hand side is our south pole because the magnetic field always points in towards the south. All right? This is probably the very trickiest part of this entire unit. So if you're not feeling great about it yet, that's okay. Look over it one more time. Feel free to get that right hand in motion, acting these things out, and we will talk about it soon. Thanks for watching.